Hello and welcome to this video for Electropages. I'm your host, Robin Mitchell. Today we're here for day 2 PCIM in Nuremberg 2025 and it's been a fantastic event. And today we are at the Novosense stand and we're here to see some pretty interesting technology. So before we jump into all of this, thank you for having us here today.
Thank
and
you.
Just introduce to the audience who you are and what you do.
Yeah, I'm Julio, the marketing from Novosense, who covering isolated products in Novosense. Yeah, mainly about the product definition and the business development. Yeah.
Fantastic. So PCIM is all about power.
Yeah.
And we're seeing some rather interesting circuitry here. So just tell me exactly what's going on here.
Yeah, so you can see over here we have onboard charger system block diagram. This is basically the onboard charger block diagram for our understanding. You can see that this is the AC input to the high voltage battery output. Basically, when you drive the car, you need the power, right?
Yeah.
So when the car is lack of power, you can pour your AC voltage in, right?
Yeah.
So this is AC voltage input, and customer may need to sense the AC voltage with the isolated devices. So we have isolated amplifier and non-isolated amplifier for the AC voltage input. And also we have the after the AC voltage input, we have the PFC stage to transfer the AC voltage to the controlled DC voltage. So here is the PFC stage here. We have 6 MOSFET for the PFC stage, and for the power stage, we have the PFC gate drivers to drive the MOSFETs. And also we will have PFC current here. So we have the Hall sensors or amplifiers to do the PFC current sensing. And then after that, there will be the DC-DC output voltage. So we will have isolated amplifier for the isolated voltage sensing here. And behind the DC output is the controlled DC to DC topology. Then we will get a very controlled and stable, like around 400 or 800 volt output directly to the battery. So this is mainly the DC-DC topology, and the same as the AC to DC topology, we will have the DC current sensing with Hall sensors or isolated amplifiers. And also we will have the drivers to drive the power stage, and also we will have the Hall sensors or isolated amplifier to do the DC output voltage and current sensing. So basically above here is the power stage, and down here is the control loop.
Right.
Yeah. For the control loop, we may need basically customer will have 2 MCUs or 2 DSPs on board, and these 2 MCUs they need communication, right? So we will have digital isolators here to do the isolation between the community of the MCUs.
That's actually quite interesting because a lot of what I'm seeing here is a lot of isolation and and I'm guessing that's down to protection and noise and signals. But it's also interesting that you're also isolating the AC side of the digital controller and then the high voltage battery side. So it's interesting. So are these isolated products? Are they new in terms of like were they released in the past year, or has it been around for quite some time?
Oh, it's been quite some time. Actually, our first generation of isolation released around 2017. But back then, we only have basic isolation. So the isolation voltage cannot be quite high. And around 2019, we have our second generation of isolation, and the surge isolation voltage can be up to 12 kilovolts.
Oh, wow.
That's when we meet reinforced isolation. That's much more high standard.
And do you think that's because battery sizes and battery charging currents are getting higher, so that's why you need these higher isolations?
Even the voltage of the battery is getting higher and higher. So before it's like 400 and now it's 800
and even that much more isolation.
So the isolation products are more and more needed in the OBC and traction inverter, basically in the automotive powertrain systems.
Fantastic. Now, if we go over here, it looks like that this is the continuation of this onboard charger.
This is the DC-DC charger. Basically, this is the high voltage battery voltage signals, and this is the low voltage battery signals.
Right.
Basically, maybe this is 400 and 800 volt, and this is 12 volt or 48 volt, right? So the topology is basically the same. You have the 400 to 12 volt, DC-DC topologies,
Yeah.
and we have the power stage here. But for DC-DC charger, it's basically only one MCUs here.
Yeah.
Yeah, so you see that basically the difference between here is only a DC-DC topology here, only one MCUs here, so do not need communication between MCUs.
Yeah.
Yeah.
And I'm guessing, again, that's because when you've got like this low voltage side of 12 volts, the
Yeah.
isolation's not as important as it is between a high voltage AC and a high voltage battery. So
Yeah,
it's
yeah.
just so much more important here.
Yeah. So you can see that the high voltage back here may need isolation,
Yeah.
but for the low voltage here may not need.
Yeah. And in that case, accuracy becomes almost more important here when you're on the lower voltage to make sure everything's
Yeah.
absolutely right. Whereas here, you can afford to have a sort of like a lower degree of accuracy because the voltage is so much higher.
Yeah, that's quite critical, right? So you can see that for this part, we may use Hall sensor for the current sensing here.
Yeah.
But for the current sensing here, we may need isolated amplifier, which have much more accuracy.
Oh, okay, right.
Yeah.
Yeah, makes sense. So over the past sort of year since you were here last time at PCIM, what challenges would you say your customers have been facing in the EV market?
Okay. So I think customer may need much higher and higher voltage, so they may need higher isolation voltage for isolated devices. This is the one big challenge. Another big challenge is power density.
Yeah.
So they may need smaller size, and to achieve smaller size, customer may need to higher their frequency.
Right.
Yeah, and they may need higher driver power for the gate drivers, and then they need smaller size for the chip. But as the voltage is getting higher, so the creepage and the clearance maybe they need higher.
Yeah.
So the smaller package must meet higher creepage. That's one of the challenges.
And that's something we've seen quite a lot around, which is that as those voltages do get higher, you need to have bigger separating in your pins.
Yeah.
But if it gets too big, then the part becomes too big, and then it makes it hard to shrink it down.
Yeah.
And so I'm guessing you're seeing this sort of like challenge where everyone's trying to shrink, but it's very, very difficult to do so.
Yeah.
But we have some really interesting boards here. Could you just go through what you've got around here?
Yeah, of course. This is the demo board we built based on the OBC system. We Novosense has systems team here. We do not only have product team, we have customer system team to do the demo board like this, to put our IC solution on the board to show to customer, hey, you can build a system like this with our ICs. So basically, this is the 6.6 kilowatt OBC solutions here, and this is the 2.2 kilowatt DC-DC solutions here. Basically, the topology is the same as the board above, just we put the BOM into the PCB board. Yeah.
So as a quick question, is this more of a reference design than an actual deployable solution, or is this more like this is actually how you could build it?
Yes, this is actually how you can build it.
And the reason why I ask is because I'm increasingly seeing more and more engineers going for this sort of like 3D structure. So instead of trying to get everything on one sort of big board, there's a lot of stacking going on. And I've noticed you've got it here, here, and here. So I'm curious as to why that's the case here.
Yeah, because you can see that there is big capacitors here. So the height must be limited to this height. Yeah. So if you can put the board like this, then the size of board
it gets shrunk
smaller.
massively.
Yeah.
And so if you try to put these on a big planar device, this PCB would be like this big.
This
now you
big.
can shrink it down and just keep it vertical. And is that something you're seeing your customers do more often as well?
Yeah, of course. A lot of tier ones of our customers are more like higher power density and smaller boards. This is the major trend we see from our customers.
Fantastic. And I see one more board there, and I'd like you to tell me exactly what's going on here, because this looks very interesting.
Yeah, this is a traction inverter system like that, but this is only the power stage. So you can see that this is basically a three-phase inverter here. You can see that we have 6 gate drivers here to build up the inverter stage, like maybe here, the traction inverter block driver.
Oh yes, right here. Yeah.
It's only this stage, the inverter DC to AC driver power stage.
What power rating is this? Because it's quite a small board.
Yeah, I think the power is only around, I'm not sure about it. Because we do not have the MOSFET here, the FETs here, we only have the drive here.
Sorry, this is the gate driver, it's not the actual power. I'm with you. Oh yes, that makes sense.
Power limited.
And so what you're showing off here is the gate driving solutions chip that you've developed.
Yeah.
And so again, this would be another design that someone can basically, sort of copy onto theirs or use it as is. and then use your
Yeah,
devices.
easy for customer to evaluate our parts.
Yeah, fantastic. And do you see how do you sort of see this kind of technology going into the next year, especially with like the rise of EVs around the world?
Yeah, we're seeing actually higher power density and higher sensing accuracy, especially to the battery charger. Yeah, so customer may asking for higher accuracy of voltage sensing and current sensing, especially when the battery voltage getting higher and higher. You can see that for isolated voltage sensing amplifier, the input voltage range is fixed.
Yeah.
Usually it's 0 to 2 volt.
Yeah.
Yeah. But with the trend from the voltage from 400 to 800, we see customers they're asking for higher input range isolated amplifier. So what we're developing is a 0 to 4 volt
Oh, right.
input isolated amplifier, and it will be coming later this year.
Oh, that's exciting.
Yeah.
And so do you think you'll be showing that off next PCIM in June?
Yeah, of course. Yeah.
Fantastic. So just before we wrap this video up, I've got one more question for you.
Yeah.
For the audience who are watching this video, if they want to get involved with Novosense solutions, what would you recommend that they do?
They can go on our website. Everything is on our website, including the data sheet, the introduction of our parts, and also we have application note on our website. Especially when you calculating the sensing accuracy, we have an AN application note on the website to tell customer how to do the calculation of the sensing accuracy.
Fantastic.
Yeah.
Thank you ever so much for having us here today.
Thank you, Robin.
Thank you very much. Thank you.